You're on the Argument Video channel, minimally valuable mathematical videos for frustrated mathematicians. This is the real analysis video series, and we're on lecture 14 on some properties of closures, and we're going to define what an open set is. Okay, so recall from the previous lecture that A is a subset of Rn is closed if there's some sequence and if that sequence in A converges to some x, then that x must be in A itself. So if there's a limit point, it must be in A. And for any subset A of Rn, the closure of A is just A bar, the set of limit points of A. So let's look at properties of closures. One proposition. Let A be a subset of Rn, then A bar, a closure, is the smallest closed set containing A. In particular, if you take the closure of a closed set, let me just add some separation between those two lines, then it's just equal to the closure itself. So it's not, don't get confused with the notation. The bar here means closure, and a double bar is just equal to A bar, which might not be the case if you use some other notation for A bar. So proof. Let A be a subset of B such that B is closed. Then the closure of A is itself a subset of B. So let X in A bar, so there exists some sequence in A such that Xn goes to X, then since Xn is in A, it must be in B. And let's use consistent notation here. So a sequence is contained in a set, and since B is closed, X must be in B, because that sequence is in B, and a limit point of a closed set must be in that set, so X must be in B as well. So we're done that claim. A bar is closed. We're going to look at this claim that A bar is closed. So let there be a sequence in A bar such that xk has limit x, and for each k, there exists some ak in A such that xk minus a of k is less than 1 over k. Then that sequence of AKs is in A, and AK is equal to AK minus XK plus XK. So we add and subtract, or subtract and add XK. So it's the same. And this difference goes to 0. And this XK goes to X. So X must also be in the closure. And we're done the proof. So the closure is the smallest closed set containing A. So some remarks. In Rn, a subset of Rn is closed if and only if A is complete. And this is true since Rn is complete, and to remind ourselves what complete means, it just means that every sequence converges to some point in that sequence, or in that set. Every sequence in that set converges to a point in that set. Now let's define something. It's a bit fundamental. It's a important definition in analysis. We say A, subset of Rn, is dense in Rn if A bar is equal to Rn. If the closure itself is the Rn. So for example, in just one dimension, the closure of the rationals is just R, so Q is dense in R. That's how you'd phrase that. Dense. Also, if you remove anything from R, then that is just R itself, because you can take a sequence 5, so plus 1 over n, so that goes to 5, which is in R, and thus is in the closure. So we're back with R again. Now for some example in Rn. The closure of Qn, n vectors where every element is a rational number, is Rn. And you can prove this using if the vector converges, then each element converges, and just extend the proof from rationals converge to R. Another definition, the open ball censored at A in Rn of radius R greater than 0 is defined to be, we've been using this notation, but here's what it's called. I've been using the name as well. The open ball is everything that is at most R away from A. So here in R, BR of A is just equal to A minus R, A plus R, which on the real number line is everything at most R distance away. So everything in here. And in Rn, or since we can't really visualize Rn for large numbers in R2, it is just, say that was A, and this was R. It would just be, whoops, everything inside, not including the outside. So I'll try to color this in carefully. Good enough. And if you take the closure of the open ball, then that inequality is no longer strict. And we call it the closed ball. Now to find what an open set is, we say A, a subset of Rn, is open if for all A in A, for any element, there's some R that is dependent on A, so where it is R is a function of A, is greater than greater than 0, such that BR of A is a subset of A. So what we're saying here is that if you have an for a set to be open, at any point in the set, you must be able to put an open ball around it of some radius. And for an example, big surprise, the open ball is open. So if you take that, then around any point in the set, you can put in an open ball of some radius. Or even if we're looking at R, let's say, A minus R, A plus R, then even if you were there's some radius that you can define so that it is inside this interval. So, for example, of a not open set, the half open interval from 0 open to 1 closed is not open, since for all epsilon, or call it R, greater than 0, if you try to put an open ball around 1, it's just not possible for it to be contained in that interval. So it's 0 at 1, then this part is not included. So no matter what radius you do, you just can't put an open ball around 1. So 0, 1 also isn't closed, since if you take a sequence 1 over n, 1 1 over n, that just goes to 0, which is, so 0 is a limit point, and it's not in 0, 1. So a set doesn't have to be open or closed, it can be neither. If we take the rational numbers, then for all epsilon greater than 0, if you take e over n in the epsilon ball, this implies that x is less than epsilon for n large enough. So Q itself is not open. If you take an open ball around 2, 3, so it's an R2, and you take the union of that with something outside of the open ball, it itself is not open. So if you have a finite set, i.e. a one element set, then those one element sets you can't put a ball around them, since they're just, let's just say this is 100, this is 87, and our other ball is 2, 3. No matter what radius you do, no matter how small you get, it just isn't in the set itself. And Rn is open because you can put an open ball around anything and just in Rn, and it'll always work. It'll always be in Rn. And also the empty set is open because if you put an open ball around any of its elements, i.e. none of its elements, then it is contained in the empty set, i.e. it's not in there. So it works. So a set can be open and closed. We showed that Rn and the empty set are closed, and they're also open. Now, if you take a bunch of sets that are open in Rn, then their union is itself open. So you can take a finite union or an infinite union and it will be open. And if you have a finite number of open sets, then their intersection is open, but an infinite intersection of them would not be. So let's prove this. Proof. A of alpha open, let A be in the union. This would mean that A is in a single one, because it's in the union. Since the set is open by assumption, you can put a radius greater than 0 ball around A itself. And since this is contained in A alpha, this would mean that it would be in the union across all alphas. So the set of unions is itself open. Now let's take A1 to AM, all open. Let there be an element in their intersection. So there's a finite number of open sets. So A is in all of them. A1 to AM, because it's in the intersection, kind of a vacuous statement. So there is an R greater than 0 defined for each set, such that the R eyeball around A is in AI. So now we will show that there is a radius that works for all sets. If we just take the minimum of all of them, R1 up to Rm, we got that the ball of that radius will be in the intersection. And so the intersection is open. Completing our proof. Now we'll give a counterexample for finite intersections being open. So if you take the finite intersection of this interval -1/k to 1/k, then it would just keep getting smaller and smaller and smaller and smaller and smaller as k goes to infinity, and that would just contain 0, which is not open. Example, if you take a union of open intervals in R, they're open by our previous proposition. And let's just work it out ourselves. So if you take 2, 3, and 8, 9, those are intervals. They're open. We know from the previous proposition that unions of open balls in Rn, which are open intervals, in this case of R, are open. And yeah, that is it. I thought I was about to say more, but I think there's nothing really to show here. We're just gonna just applying that proof. So I guess if you wanted to see a picture, take 2 and 3, 8 and 9 on the real number line, take the open interval, so the union of them. Then no matter what point you have, you can always put an open ball around it, because the union doesn't really affect things in restricting the elements in them. And that is it. Thank you.